Welcome back. The architectural design process keeps moving forward, and now we're at schematic design, which I would argue to be one of the most difficult parts of the design process. Okay, so why an A3 building classification? In my studies, that was the most prevalent type of building type that we had to do for studio projects, so I thought the likelihood of you needing an A3 was the closest. And I'll be referring to, once again, 2018 International Building Code. So let's start by getting this Rhino model into Revit. What I did is I took my concept and I broke it into cores, program, primary structure, and then some screening or secondary structure. And this just gets me roughly into the concept that I want to do. I plan on being a little bit more elaborate as if we go into schematic design and design development. All right, so here's how we're going to do this. I'm going to take the cores. I'm just going to export it as ACIS file. So here's the cores. I'm going to right click and say select objects. There's my two cores. Then I'm going to go to file. I'm going to say export selected. And I'm going to go and export that into a folder that I have all ready for myself. And we're going to drop down and change that to an ACIS file. There it is, .sat. And from there, we can just say save. All the default settings are what I have. And the name, which we have to give it, I'm just going to call it course and say save. Select objects. Primary structure now. And then lastly, the screening. Okay, so now that I have all of those elements as ACIS files, we can't do 2D line work as ACIS. We're going to need to do that as AutoCAD. So for my site information here, I'm going to unlock that. I'm going to go to my site boundary, which is that yellow line that you can't see. Let's go and change that real quick to something that's a little bit darker. Let's just do a black line and say, okay, there we go. Now you can see it. So I'm going to go and take that boundary, select object, and then I'm going to export it as a DWG AutoCAD file. Now I have that out. I'm going to go and lock my site information again. I do want to show you in relation to the origin where my site boundary is. That's going to relate to where the blue circle is on the site plan in Revit. So in Revit, we go to our site plan. Let's go and import in our site boundary first. By going to the Insert tab, Import CAD, go to the folder that you have it in. We're going to be looking for a DWG file. We're going to pick the site boundary. I can say current view only, or I can make it so it's in all views. I'm just going to keep current view only for right now. I'm in my site plan view. Everything else by default should be fine. Just say open. And here you're going to see that that blue circle relates to where the origin was in Rhino. So here's our site. What I might want to think about doing right now is take these elevation markers and move those over so they represent the center or closer to the center of where my building's going to be. Let me go and take this one, just slide that over, take this one, move it on up. I'm trying to move them straight so they're still straight across from each other. Okay, so something like this looks good to me. I'm going to go and save that. Now we're going to go and import in. Let's do it in 3D. We're going to import in the rest of the stuff. Let's bring in a few of the ACIS models. So I'm going to go to Import CAD and I'm going to go to search for the ACIS files within the folder I have them saved. The program, I want to show you something a little special with that one, so I'm not going to bring that one in yet. Let's go and bring in the cores, and we can bring it in as a category of a generic model, or if we had something specific that we wanted to bring in. What's nice about this is for our visual settings, our VG, visual graphic overrides on the views, we can make them associated with these categories, which is nice. So I'm going to just bring this in for now. Okay, say open. Oh, so one thing that I didn't note is that these right now are associated with top of footing. So let me go and bring that in again. Import CAD. Here's the cores. I can say they are going to be placed at finished floor. Open. All right. If I go to the right side view, you'll see where they come in at, right? Finished floor. And we're going to go and bring these in though at the right height. Open. There it is. And let's go and bring in some other items. So import CAD. We'll do the screening. Once again, get the correct height. All right, so this just gets us started, right? It's just a starting place. We might end up changing this or whatever, but we might even remodel it, delete it out so it's more workable in Revit. But for now, it's a placeholder and it's getting us closer to what we want. Speaking about what we want, we're going to end up making a family file. Here's another workflow for you. And we're going to use Rhino inside to import the geometry just so you can see something new. I'm going to go to File, I'm going to go to New, and I'm going to say Conceptual Mass. And this mass we're going to bring into Revit, and then we're going to mass floors with it. Conceptual Mass has a mass.rft family file that we can go and open. This creates a new family file for us. The Rhino Inside tab works here as well. So I can go there, and then I can go to Grasshopper, and I have a script that I made. And so this script here uses the geometry direct shape. So up here in the Revit tab under direct shape, I did geometry direct shape. And then I dragged that in just like that. And then here we have the name. So if you double click and type // then you can type a name. So here I typed in program. So it's my volume for my program. This is just a text field then, and that can be imported into name. For the G, that's geometry. Double click and type brep. And that can reference a brep from a Rhino model, which I have open in the Rhino Inside Revit tab. So basically here, Rhino Inside, I went to Start Rhino, and that's where I opened up my Rhino file from the concept design. And then now I can refer to this with my Grasshopper script for breps. And all right, so then from here, I'm going to give it a model category. So that was direct shape, drag in your model category. And here you can double click and search for any kind of category you would want to reference in Revit. And that will assign it here into this shape, this geometry. So I'm saying generic model. I can go and make that into a mass as well. It doesn't really matter right here because I'm using a mass family. So I'm going to make it a generic model to keep it simple. And then that mass family will end up making it a mass in Revit, if that makes sense. So again, double click type material, assign it to the material category, then right click on that. And here we can go and change it to a material that we would like. And default is just fine for right now. Okay, so that then creates this direct shape. It should, when it likes it, turn black. That should make it automatically in my massing file here. And if we don't see it popping up, turn it off and on by double clicking the category once and twice just to re-jog it to make it think again and process again. And now that I have the forms in here, you can see that they're also referencing the origin, same as before in Rhino. So everything's going to be aligned as I bring this in. I can say load into project and close. I can also save this as a program mass for this project. So I'll go and do that too. So let's go to a save as family file, and I'm going to call this program mass. Save. And then I'm going to load into project and close. This will load into my current project if only one's open. Otherwise, you'll have an option, a menu to select from. That's cool. Say close. Now, you have to manually place this, but no fears. Just snap to that circle. That's the base point. Hit escape a couple times. Now, if I go and click on it, we can see in 3D, this is exactly what we had in Rhino. Everything's placed perfectly. It's important to note that when I brought in this mass through the mass family and I used Grasshopper, I also could have loaded my ACIS files into that mass family and brought that in that way. Or what I could also have done is run the Rhino Inside tab right away and brought my Rhino model directly into Revit this way as well through the Grasshopper. So you have options, right? You have options to bring in your model in many different ways. Now, by bringing it in through the mass family, what's nice is when I click on it, I can click on mass floors. So if I have my elevations set up ahead of time, I can mass floors at those elevation lines. And what this does is it's going to give me an option to mask these different planes. I'm going to just choose these finished floors because for my purposes, I'm going to use those areas to help figure out what my square footage currently is. So if I go and click on one of those, so for example, I'm clicking on the finish 3, level 3 floor. Here I can get my floor area calculated for me rather quick. So here I'm at 19,447.99 square feet. So this is already well beyond where I was intending to be. So I know I need to scale this down by a bit. So I'm going to go through, make some modifications and changes. I'll speed up the video for that, and then we'll be back. Okay, let's see how I did. So I brought in, I went into Rhino, I scaled everything down, I re-exported new ACISs, and I also re-imported the mass. So with this mass, let's go and see it. Mass floors, give me 1, 2, 3. Okay. Now let's go and check those. So floor 3, we're at 1,000 square feet roughly. Floor 2, 4,400 square feet. And the last floor here, let's see if we can get selected. Hit tab to grab that. And we're at 4,400 as well. So now I am right on point with where I want to be. So I'm happy with the size of the mass. I'm overall happy with the general form. So at this point, I have some decisions to make. In the massing and site tab, I can either use floor by face and use that to place floors on my slabs that I have here. I could also use roof by face and start to cap off the tops of my roofs here. And I can use wall by face or curtain system by face. And I can use that to get some of this geometry into Revit elements. Or I can just go and draw these myself. I find it most flexible if I go and do floor by face and then build everything around that. So I'm going to do floor by face. I'm just going to pick a floor that I want to use. So here I have some cross laminated timber floors in this template that I have pre-made. And I'm going to say create floor. So now I have those floor systems made. And with this, I'm going to build everything else around it. I don't think I'm going to use the rest of the mass in this project. So I'm just going to go and kind of go freestyle from here. So this volume here, what I'm going to do is just hide this. And I'm going to hide it. It's a hide in view element. And I might delete it later, but for now I'm going to do that. Okay, so I have those hidden. And from this point on, I'm just going to go through and draw out the rest of the model. So I'm going to go a little bit faster. After I draw the model, I'll explain all the code that I'm considering as I draw it. Okay, so let's draw some column lines and then we'll talk about some of the decisions that I made based on some code requirements. So up here in architecture, I'm going to go to the grid line, and the first grid that I'm going to do, I'm going to draw one that goes along this back wall in case I end up wanting that to become a column line. So I'm just going to go and click, come across and click, hit escape a couple times. I'm going to use the copy command. If we check the box on one side versus the other, you'll see that it'll snap the bubble to one or both sides. You should have at least one of the two on. We're going to go and copy. We're going to come down and copy where we would maybe want another grid line to be. I'll do the same thing coming down and coming down. So here I'm placing them on the inside edges of the wall. Okay, so that's how I'm laying these out in this fashion. And then I also want to include some column spacing on where these kind of column beams exist. So we'll do the same thing, go to the grid, and I'm just going to go from the center up. Now this one here, and I'm going to just try and copy these over. I'm going to go just from midpoint to midpoint. And then from here, I have one column grid that's going to be on an angle, so I'm going to throw that in too. And I think I'm going to name this one 3.3.8. The reason I'm naming it 3.8 is because it follows, in my mind, more on this vertical relationship going this way. So now I have my column grid organized. And later on, when I get into design development, I can fine tune this a little bit more, but that's what I have for now. Okay, so let's define the egress system. It's broken into 3 spots. You have the exit access. That's the path through the building, through the rooms, through hallways that aren't completely dedicated to just exiting the building. Then we have the exit. That's enclosed areas such as this stairwell here. That is 100% top rated for the building on fire protection. So normally a 2-hour fire rated wall, 3-hour, 4-hour. We'll be using a 2-hour in our project here. And so that's completely enclosed. Floors, walls, roof, ceilings, doors, anything in this volume is enclosed with a 2-hour fire rated protection or better. And then that's an unlimited distance that we can use to get through the building. This is also where we can have areas of refuge. If you're in a wheelchair or you're disabled and you have a hard time getting downstairs, this is where you could wait for a firefighter to help you get out of the building or somebody else. And then we have the exit discharge. And this is the path that is beyond the exit, allowing you to get to public safety, street fronts, sidewalk, public right of way. So let's take a look at our project and see where some of these numbers apply. So right here, if we're going to be looking at our exit access, on the first floor, it's relatively simple. I have a little component here in this template called path of travel line, which is going to calculate my path of travel. So we're trying to find the area in the building that is furthest away. And it could be kind of coming out of the bathroom, this kind of area here. Now, if we're doing this, let's just start right here. I believe you don't have to use the bathroom as the main, like the farthest place, because that's not a place you would be dwelling. And so we'll start just beyond that. And we're supposed to not go diagonal through the spaces. We're supposed to just kind of line that up like so. All right, so I have these lines. And what I'm going to do here is just hold down Control and pick on all of them. And I can label them. So I'm going to label it A, apply. And then I have a egress path of travel schedule. So distance A is 88 feet and 9 inches, roughly. So I'm going to go down this way. There we go. Getting out. And this should be all path B. All right, there we go. So now let's take a look at that schedule. And path B is 85 feet. So slightly closer, but not by much. Now, regardless, the numbers that we can use here for an A3 building classification is we can go a maximum distance of 200 feet if the building was not sprinklered. We're going to use sprinklered, so we actually have up to 250 feet. So that means both of these egress path of travels pass the test, which is great. So I'm going to go and just keep those lines on there for now. We're going to go to the next floor. So let's go to floor 2. So floor 2 is a little bit different. We have some stadium, some fixed seating. And so we'll talk about the common path of travel and what our distances are for that. Okay, so let's talk about two different kinds of assembly seating. You have continental seating on the left, and you have conventional seating on the right. Continental seating, just real quick, wider row spacing, longer row lengths, less aisles, more exits. And then conventional seating, we have tighter, narrower row spacing, shorter row lengths, more aisles, less exits. So if we look at conventional seating a little bit closer, since it's a little more intricate with how it lays out, both of them have something called clear row spacing. And so to help illustrate what clear row spacing is, let's take a look at this diagram. Now you can have seats that are self-rising or not. Regardless, they create that clear row spacing, the ability to walk in between the seats, mini aisles, let's just say. So with this, the length of the aisle and the clear row spacing all kind of comes together with aisle access. So if you have 2 aisle access, that's 100 seats max per row, 12 inches between the rows. And then there's a penalty of 0.3 inches of clear row additional space required for every seat over 14 in the row. And that caps at 22 inches max between the rows. And that is also common, that cap with single row spacing. But in single row spacing, you are limited not to 100 seats, you're limited to the common path of travel, 30 feet. So the wider your seats, the less you can fit in. 12 inches clear between the rows, and then 0.6 inch penalty for every seat above 7 in the row. Once again, capping at 22 inch max between the rows. We're going to go to a spot here on the diagram that is a little bit better at illustrating the different ways you can access an aisle. Here's an aisle loaded from just one side, and then over here on the right, an aisle loaded from 2 different sides. So aisles and ramped aisle widths. Aisles that are sloped more than 120 are considered ramped aisles. And so you'll see below that ramped aisles have a minimum of 36 inches, no matter if they're served from 1 or 2 sides. And then they also require a 48-inch width if they are served from 50 seats or more on 2 sides. Aisles themselves, serving 14 or less, have a 30-inch minimum width, so a little bit less than ramped aisles. Serving seating only on 1 side or less than 50 seats on 2 sides, 36 inches in width. Serving 2 sides, 50 or more seats, 42 inches, may vary in width only if serving rows from 1 side. So it can taper in or out. Aisle slopes, it's important to note these thresholds, so I kind of clustered these together so you can see where the thresholds are and what those benefits would be if you go on the less steep side at that threshold. And so basically just think in general, the more extreme the slope, the more restrictions going to apply because it's going to be more difficult for people to navigate a steeper sloped aisle. Dead ends, maximum distance 20 feet, but there are exceptions. You can look those up in code. Accessible wheelchair seating requirements. Rule of thumb, just keep in mind the larger the total capacity, the more seats, the more wheelchair seating you need to have available. And then stairs themselves have a 11-inch minimum tread depth, a 48-inch rise. Sometimes 9 is permitted if necessitated by adjacent seating, and then widths same as ramped aisles. So there you have it. That's egress for assembly seating, and it's not so bad if you digest it in chunks. And I would just think about, the thresholds throughout this. You can go on the very conservative side, or if you need to fit a lot in a tight space, take into consideration what your options are. All right, we're moving on. And I'm going to turn off underlay right now because that is making this look a little bit more confusing. There we go. And I'm also going to hide these for right now. All right, so let's go back to our component. Now here, arguably, the deepest spot might be here. Call this path C. And so if we're on the landing, then let's go and take a look at plan 1. So that's all path C. So let's find out how path C did on our Egress path of travel schedule. Path C is 160 feet. That's not a problem. And let's go and take a look if we make a path D. The reason I chose here is because anything closer I could have wrapped around this way. So I'm going right about here. So if there was a fire this way, maybe this is the way we would exit. And that gets us to our exit. So once again, path C and D are going on our exit axis, and that's leading to our exit stairwell. So once again, going to the schedule, path D, 73 feet. So not a problem. Now this building is 3 stories tall. On the 3rd story, I'm making it just for employees, not for the rest of the public. So I have just one stairwell here, and that's because there's really not a lot of people that are designed to be up here. And so it's kind of looked at as one room that has immediate access to the stairwell. I have fire-rated partition walls here. This would be a fire-rated door. And so this becomes an extension of that exit going straight down. Notice the doors all swing out. That's required by code. This door is for, storage, mechanical space, maybe a server room. This is a room that's dedicated towards fixing VR headsets, technology, computers. So there's some workstations, cabinets, etc. So that's why this is designed like this. Then here we have just to explain what's going on, we have a little cafe with the service counter. And we have some stadium seating to watch potentially on a screen or a performance of some kind in VR. So just kind of a cool little stadium environment for that. And we could take a look at that in 3D. Something like this. And then on the first floor, still being fleshed out. We'll do that in design development, but thinking some kind of VR spots, gaming spots down this main corridor. And then there's some computer desktop gaming as well. Some areas for that. So probably find a way to incorporate some more of that, maybe along this wall here too. Now, what we want to do is also define a couple of other things. And so we're going to talk about sizing, and we're also going to talk about common path of travel. Both are pretty important. So let's first take a look at common path of travel together. So this is an example of being in a far corner of a room, and you need to travel all the way through the door of that room and up to be able to then have 2 options to get out. So think of common path of travel in a sense of you're in a room. It's not necessarily a dead end, but you're as far back as you can go. And until you have 2 options, you're at risk, because if a fire starts and you're too deep in a room, that thing might spread, you might not notice it, and then all of a sudden you have no options. So we have a certain distance before we need to have 2 options to be able to get out of the building. So for example, the common path of travel is 75 feet for all spaces in an A3 sprinklered building, unless there's 50 or more people with fixed seats, then it's 30 feet max. So knowing that, let's go back and take a look. So here, I don't have any fixed seats at the moment in this room. So we have the 75 feet. And to be honest, there is no space here, other than maybe this office space, that doesn't have 2 routes almost immediately, right? Like the bathroom's the office. Every other space you're in, you can egress out the front door or this emergency exit only. So it feels like a pretty good design on the first floor for that. But the tricky part becomes the second floor. You can exit out the back of this. Maybe we should see this in 3D. You can exit out the back of the stadium seating in this case, as well as here's the ramp down the back, as well as the front. And so there's 2 exit access points. So the common path of travel is as small as I could make it on the stadium seating. So now let's take a look at the 3rd floor. The 3rd floor, we have 1 path out, but that's immediately to the exit. So we are fine. We take a look at that in terms of measurements. Let's go and drop down one more path of travel line, and we'll call this one letter E, just to be thorough. And let's just say this guy is looking to get out. That's what we have. And if we take a look at our schedule, E is at 41 feet. So we're good. We are less than 75. So just real quick to recap, we have our common path of travel. If it's fixed seating, 50 people or more in a room, 30-foot max for common path. So that's until you have two options. And then for all other spaces, 75 feet. The actual exit access, so moving through the building until you get to a dedicated exit that is fire protected, you have 200 feet if your building is unsprinklered in an A3 building classification, 250 if it's sprinklered, and 400 feet max if it's open aired. But in essence, that's the name of the game. It's all about the exit access, in my opinion. So sizing the egress. So exit doors are sized based on the occupant load. So you can have an exit door, 49 people or less, 36-inch minimum, 50 people or more require two exits, and 44-inch minimum for that path. And that's the same with stairs. So the stairs I have drawn, let's take a look. The actual run width is 3'10". That's 36 plus 10, so that would be 46. So that should be good, but let's take a look at what that clear distance is. Between those handrails, looks like it's only 3. So I might need to address that on my egress stairs here. Now clearly there's more than 50 seats here. Let's see, select all instances and view 202. Yeah, so there's 202 seats there plus these ones, right? So we can select all instances, view 28, 202 plus 28, 230. So potentially 230 plus whoever might be up on here, maybe some standing room. So this is heavily occupied. So I need to make sure I size my stairwells accordingly. So my doors, my sizing, my spacing, all has to be updated. This room requires 2 exits, and so I do have them. Dead ends, maximum of 20 feet or 2.5 times the width of the corridor. And in this building layout, I don't really have any dead ends, right? Floor 3 is just one room. Floor 2, one giant room pretty much. Now here, this looks like what could be a dead end, but this is actually not a corridor, so it does not count. This is a room. So this room is a common path of travel that we see through here. So that would be using the 75 feet. So we're fine. Dead ends refer to corridors. So corridors are taking up load from other rooms. So that is all good there. Let's go to our first floor. Our biggest dead end is this little guy right here. Let's just go and measure that as this depth right here, about 10 feet max. So this is designed purposely to not have any dead ends. But if you did, those are your rules. 20 feet or 2.5 times the width of the corridor may be the depth of that dead end. Let's take a look at the distance requirement between exits. So if we go and measure, let's just say the entire space, so that's D prime here, then the distance for little letter D prime needs to be a third or half of distance D. So basically the distance between the actual exits need to be at least 1/2 or 1/3 of the space that they serve. So let me show you what that means in this case. So if I go and take a measurement from the door to the door, that is 108 feet and 8 inches, at least half or a third or more of this distance. So 126 feet, 11 inches. And so if I just did 126 and 11 inches divided by the distance that these are apart, 109, I'm going to be well above half that distance, which is good. The idea behind this is that one fire doesn't block both exits at the same time. So we do need these 2 exits to be spaced out enough for them to be considered 2 different exits out of the building. Similar to sports, right? Let's say playing basketball on the offense, one defender can guard both guys if those 2 guys are too close together. So the idea is to spread out enough where one fire can't block both exits. For the actual, like let's say we had a room that needed 2 exits as well. So if we had one independent room, which I guess would be this one in this example, you would be doing the same thing, right? A room with 50 or more people requires 2 exits. So you would do the diagonal of the room that it's serving. So here's the diagonal of the room that's being served. That's 95 feet and 7 inches. And then we want to make sure that the actual exits are at least half of that. And this is 86, so that's definitely more than half. All right, cool. So that's separated enough as well. The idea that I try and do is just put them on opposite ends. Just think like any hotel that you've been in, right, is probably a double stacked corridor. So you got rooms on either side of the hall, and capping off the ends of that hall is typically an emergency exit stairwell on either side, which basically guarantees that you have a really short common path of travel and you don't have any dead ends with that kind of design. So I highly recommend doing something like that to keep things simple if you are new to this. We are just looking at how you would be clicking through to measure. I mentioned this before. We're trying to avoid diagonals on our routes. These kind of straight bouncing around pathways, I think, add a little bit of additional length to the path. So if you do have a complicated room with some obstacles, this helps account for that in my mind. That's how I remember to do that. It's more conservative. Here's an example of the corridors capped on either side with stairwells. And then here's an example of dead-end corridors in the shaded areas. Right? So 20 feet max, or 2.5 times the width of the hallway. Okay, so structurally, here's what we can do. In schematic design, we can dial in some rule of thumb here. So what I have is a span and depth chart in front of me. And what you're seeing down the left-hand column here are the different types of wood structural members. And here we have a legend and a key, but I'll just explain it to you. Next to that is a column that shows the general geometry of a profile, a section cut through that structural material. So for example, laminated beams, we can see it typically takes the formation of a rectangle that is more deep in the z-axis. And then the approximate depths. So what this means is the length of the beam that we're using. The rule of thumb is the depth will be, in this case, a laminated beam will be about 1/20th to 1/18th the depth of the length of the beam. So for example, if it's 20 feet long, we would divide 20 feet by 20, and then that would be a 1 foot deep beam to span 20 feet. Same thing then for laminated arches. You've seen in my concept that I'm using some basically arches in my design. And so we see that as much deeper. So once again, 20 feet, not the typical span for an arch, but let's say we're going 60 feet on our glue laminated arches for this design. Then we're expecting to then take that 60 divided by 6. That might be 10 feet deep at some point. So there you have it. That's how you read a span and depth chart. And I'm hyper focusing on laminated beams in this case, and also laminated arches. There's also a rule of thumb. You can pretty much take the glue lam beam length, once again divided by 20, and that's your depth. But if it's going to tie into, let's say, a girder, you just add 6 inches to that, and a 6x6 glue laminated column. So an engineered 6x6 glue lam column can carry approximately 600 square feet of roof and floor area. So there you have it. There's your structural preliminary calculations, kind of ballparked for you. So one more thing to include with your preliminary structural calculations is to make sure, especially if there's a significant floor depth to your structural system, that you include that in your floor to floor heights. So that way you can maintain the actual heights of the floor to ceilings that you wish to have. So if I'm using a laminated arch that might add 4 feet to 6 feet of depth, let's say at its thickest point, I need to make sure that I'm incorporating tall enough floor to floor heights to maintain the aesthetics and the geometry that I want within my design. If you found this video useful, please make sure to like and share it with someone else that you think might also find it useful. Also, don't forget to check out our website. The link's below. You'll find apparel and other resources that you might like. If you want to purchase the Architect Studio Companion, the link is also below. That was often referenced and utilized during this video to provide you the information. And please join me in the next video as we tackle design development, where we are going to modify our drawings to achieve the aesthetics and architectural qualities that we want our design to embody. Thanks, and we'll see you next time.